become a major contributor to the food bank here in Food Parish. All right, folks. Let's see. Last time we were looking at resistors in series and in parallel. Let me just recap the rules for each of them. So you should have this written already in your notes. So let me just recap them here. Just put them all in one place, just to sort of help to jog your memory. For resistors in series, goodness bless you. For resistors in series, you have several rules. One is the equivalent resistance is just equal to R1 plus R2, plus however many resistors you have. The second is that resistors in series have the same current. The third is that the potential is equal to the V1 plus V2, just like we had for capacitors. And then the fourth is just Ohm's law, V equals IR. Right. And then for resistors in parallel, we have similar rules. One is the equivalent. It looks like the equivalent capacitance for capacitors in series. So be careful, they're switched between capacitors and resistors, the way you calculate those. But they're on your equation sheet. Resistors in parallel have the same what? They have the same voltage, right? Thank you, Chris. The third is that IN equals I out. By the way, this rule is called the loop rule, and this rule is called the junction rule. We'll use those a bit more. Collectively, those are called Kirchhoff's rules, which we'll see later. And then finally, Ohm's law also applies. V equals IR. All right, so those are sort of basic principles or basic rules for series and parallel circuits. Let's look at a simple parallel circuit. So I have this circuit. I want you to find the currents and voltages for each resistor, the total current, and the equivalent resistance. So why don't you go ahead and get a little head start on that. What are the voltages? What are the currents? What's the total current? And what's the equivalent resistance? In that order is easier, answering them in that way. So there are several ways you can answer it. What are the voltages, the currents, the total current, and the equivalent resistance? All right, so the voltage is the V1. You might have a knack for what that is, V1. Right, these are in parallel, so they have the same voltage. So V1 is equal to 10 volts, and V2 is also 10 volts. I have 10 volts on each of these because they're in parallel. Resistors in parallel have the same voltage. They have the same voltage as the battery. And then you can use Ohm's law to find I1 and I2. I1 is 10 over 2, right, which is equal to 5 amps. I2 is 10 over 4, which is 5 halves amps, 2.5 amps. What's the total current? Can I tell me? Taking that rule, I think it was rule number 3 that we had.
What was the question?
What's the total current?
The total current is 5 over 3.
5 over 3? No. It's going to be 7.5. Because I know if I have 5 amps here and 2.5 amps here, or 5 halves amps, then this current coming in, the incoming current, has to equal those. So I has to equal I1 plus I2, and that's going to be 5 plus 5 halves, which is 7.5 amps. I'll show you an alternate way to get that in just a second. And then finally, the equivalent resistance is equal to 1 over 2 plus 1 over 4. I think, Jose, this is what you were saying, right? The equivalent resistance. Yes, that's 2/4 plus 1/4, which is 3/4, so it's 4/3. Is that what you were saying?
No, I was saying something else.
Oh, okay. All right. You should just say yes. That was what I meant. Okay, so the equivalent resistance is 4/3. Now, an alternate way of finding that total current, I know that that circuit is equivalent to this circuit. I have 4/3 ohms right here and 10 volts right here. So I can find the current in that circuit, which is right here. That's going to be the same current as up here. It's going to be V over R. That's 10 over 4/3, 30 over 4, which is 7.5 amps. So you can find the total current in two separate ways. This is a pretty simple circuit. You could see something like this on the multiple choice part of the exam, which is, I guess, in a couple of weeks or so, but probably not in the free response. You'd have a more complicated circuit. Once you're in parallel, they're pretty simple because you know that they have to have the same voltage. Am I able to get this okay? Now let's try another one. Can I go down? Let's try this. We'll have a series of quicker questions here. What happens to the voltage in each resistor as you add resistors in parallel? Does it increase, decrease, stay the same, or does it depend upon the added resistance? That is, what happens to this voltage, for example, if I add a resistor there? And as I keep adding resistors, what happens to that voltage? I'll stop at 45. Oh, we have 16? I thought we had 15. 3, 7. Oh yeah, we have 16. Oh, we have 17 now. Okay. All right, C is right. Because resistors in parallel have the same voltage, it doesn't matter what resistors you have, they're all going to carry the same voltage. This is like our household, right? So all of our objects, or all of our devices, our toaster, our hairdryer, our radio, our clock, those are all in parallel, so they all draw 120 volts. And if you plug in an additional thing, it doesn't cause the voltage for another thing to drop. That would be kind of random and difficult to design electrical devices for your house if that was the case. That would be the case, by the way, if this was in series instead of parallel. What would happen to the voltage in each resistor as you add resistors? Let's try it. So if instead it was a circuit in series, what would happen to the voltage in each resistor as you add resistors in series? All right, I'll stop at 40. All right, very good. The voltage would decrease. As you add them, the equivalent resistance would increase. That would cause the current to decrease through the circuit, which would cause the voltage across each resistor to decrease as well. And so if your house was that way, that would be difficult to deal with. See, we'll come back to this, but let's work on some more of these sort of conceptual questions. We haven't done these yet, have we? We haven't started these. All right, these are in the back of your book if you want to follow along there. You have a 9-volt battery with 3 identical resistors. What is the potential across each resistor? Again, you could see questions like this in the multiple choice part of your exam coming up, not in the free response. These are 3 identical resistors. Stop at 1 minute. 1 minute. Right, C is the right answer. That was 3 volts, right? C 3 volts. Yeah. So since they're identical, they all have the same voltage. So I have 3 volts here, 3 volts here, and 3 volts there. 3 plus 3 plus 3 is 9. Oh, in the circuit below, what is the voltage across R1? What's the voltage across R1? Remember V equals IR. So if R is big, I'll have a bigger voltage. Our current remains constant. And I'll stop at 50 seconds. 50. Very good. A couple different ways you can look at this. You can see that this resistor is twice that of the other. So I know that the voltage has to be twice, but it also has to add up to equal 12 volts. So that has to be 8 and 4. We've seen that before, the way they're distributed in that way. Another way, sort of the all-purpose way that works everywhere, is you can find the equivalent resistance, which is equal to 6 ohms. That's just 4 plus 2. And then I find the total current, which is 12 over 6. That's 12 volts over 6 ohms, V over R, 2 amps. That tells me that I have 2 amps here and 2 amps here. 2 times 4 is 8. 2 times 2 is 4. So that's sort of a good all-purpose way to find the voltage. But as you know on the test, I'll try to give you nice round numbers so that you don't have to go through the calculations. What is the current through R1 here? Stop at 50 seconds. 50. Okay, very good. They both have the same voltage. They both have 10 volts. 10 volts. That means I have 2 amps here and 5 amps here. What is the total current of these 5 options? What is the total current? That is the current coming through here. Yeah, click. right, I'll stop at 35. All right, points P and Q are connected to a battery of fixed voltage. As you add more resistors to the parallel circuit, what happens to the total current in the circuit? This is similar to what we had before, but here I'm asking about the total current, not the voltage on each resistor. As I add resistors in parallel, what happens to the total current? I'll stop at 45. Okay, so remember all of these have the same voltage, right? And let's just say they're all identical resistors. So they're also all going to have the same current. And then as I add resistors, I likewise get the same voltage and the same current. And so as I keep adding resistors that both have the same voltage and they also have this additional current. So I want to know what happens to this total current here. As I add more resistors, what happens to that total current in the circuit? That current coming off the battery. All right, I'll stop at 35. Okay, the total current will increase. So A is the correct answer. This happens in your house, right? Like every morning when I get up, I turn on the microwave because I heat up my coffee. I make coffee like for the whole week, and so I just keep it in the refrigerator, and then in the morning I'll heat it up in the refrigerator. That's more information than you really needed, but that's, yeah, it's a lot easier. I hate making coffee in the morning.
I like brewed coffee.
No, it's just as fine. You put it in the fridge, man. It'll keep all week. It tastes just as good. That's beside the point. But like if I turn on the microwave and the heater, like we have a little space heater in our kitchen because it's cold. If I turn on the microwave and the heater, it always kicks the circuit breaker off. And that's because as you add these devices in parallel, your total current increases. And in your household, you have the circuit breakers that protect your circuits. If you exceed a certain amount, those circuit breakers will turn off. And so that's what happens as you add resistors in parallel, your total current increases. So A is the right answer here. Current flows to a light bulb. If a wire is now connected across the bulb, what happens? And we'll assume that wires have a resistance equal to 0 ohms. That's not entirely true, but we'll assume that that's the case for this. A resistance approaching 0 ohms. Nothing can really have a 0 resistance. I'll stop at 110. 110. goodness. Okay. So electricity tends to take the easiest path. The path of what? Least resistance. That's where that saying comes from, actually, from electrical circuits. That you'll take the path of least resistance. And so electricity here are your charges. When they come along here, they'll get to this point and they'll say, I have a choice. I can either go along the wire or I can go through the light bulb. And since they're charges, they always want to take the path of least resistance. So the charges will choose to go this way. Or most of the charges will. They actually are proportioned based on the resistance. So most of them will go through the smaller resistance, and then some will go through the light bulb, which has a much larger resistance. But here, since we're saying that the resistance goes to 0 of the wire, they're going to all go through the wire. So it's basically like removing the light bulb altogether. Lauren? It would go to infinity? Yeah, that's a very good question. You have to assume that you have some sort of resistance, right? Or that doesn't work, right? Because she's saying, well, I is equal to V over R, so if R is equal to 0, then that means that I goes to infinity. It's undefined. It's undefined.
But it tends towards infinity.
Right, it tends towards infinity.
Because you can't find a number at infinity because you have to stop at something.
Okay. You have to assume that there's some resistance. And like in this case, we would assume that somewhere further along the circuit, there's a resistance that's dictating what that current is. Does that answer your question, sort of? Yeah. That's a good question. Okay. Two bulbs A and B are connected in series to a constant voltage source. When a wire is connected across B, bulb A will do what? So it's asking, if I close this switch right here, so that's a connection, what happens to bulb A? Brighter, same, dimmer, does it go out? How does it explode? All right, I'll stop at 1 minute. 1 minute. All right, very good. A is the right answer. The voltage, like let's say that we have 10 volts here. With bulb B, we would have 5 volts and 5 volts on each of them because they would split it. But when you take bulb B out of the picture, now I'm going to get 10 volts across bulb A, delivering more energy to that light bulb, that device, because remember voltage is a measure of energy per charge, and producing a greater amount of current, providing more power to that bulb. So it'll glow brighter. And bulb B, of course, would just go out. Now, which of these circuits produces more light? 1, 2, the same, or does it depend upon R? So the R of each light bulb is identical light bulbs. Yeah, who's that?
Can you say that that's bringing all 4 of them?
Right, so this has R, this has R, R, R. All right, 5 more seconds. I'll stop at 1 minute. Very good. So if circuit 1 is producing more power, and that's true, they both have more potential across each of them. So I have 12 volts, but I have 6 and 6 volts here. Why is that? Am I just having a more efficient circuit so that I get more energy out of it, or what was happening to our battery here in both situations? What's the difference in the draw on the battery? Let me just tell you the answer I'm looking for.
Each of the section of voltage.
Okay, well, we can think about it this way. This circuit is pulling 2 amps, right? If I imagine that this is, if this is 12 ohms, let's say this is 12 ohms, then this circuit is pulling a max of 2 amps. Whereas if both these resistors are 12 ohms over here, I'm only pulling half that. I'm pulling a half an amp through that circuit. So your battery in the parallel circuit is going to be exhausted more readily. You're drawing more energy off of it, and that's exhausting the battery. So whatever the battery operates on, be it chemical energy or whatever, it's exhausting that power supply more quickly. Right? That energy doesn't come from just nowhere, I mean. Right? Right. Right. Okay. Just a couple more, and then we'll move on to other stuff. Remember here your power expressions? I'm going to write them here for you. You first might want to ask yourself, is bulb B brighter or dimmer than bulb A? And then you can get rid of some answers. All right, I'll stop at 155. 155. Okay, well, it is either C or D, right? Because we know that bulb B has to be dimmer. So it gets rid of A, B, and E, right? So it's either C or D. Now notice here that the voltages here are half. So here I have 5 volts, but up here I have 10 volts for reasons that we've shown before. That bulb B and C are splitting that 10 volts of potential off the battery. All right, so you might be inclined to say, well, I have half the voltage here. But you need to ask yourself also, what happens to the current? How is the current affected in bulbs B and C? Can we try it again? The current is not constant between bulb A and bulb B. So you want to, when you're looking at this, you want to pick the expression that has only one variable and one constant value. stop at 55. 55. Okay, D is the right answer. Because my current is also going to change by a factor of a half. And so if I look at this first expression, I get a half times a half, which gives me a quarter of the power in bulb B as compared to bulb A. But notice here, like if I take this expression, my resistance is constant between bulb A and bulb B. That's the same, but my voltage is changing by a half. And so that also gives me the quarter factor. Similarly with that third expression, the resistance is constant, but the current is changing by a factor of a half, so that gives me that 1/4. Yes? Not exactly? All right.
Can you do it plugging into numbers?
What's that?
Can you do it plugging into?
Sure. Yeah, so let's say that these are all 1 ohm, right? So I have, if I have 5 volts over a 1 ohm resistor, that gives me a current, I is V over R, so 5 amps. So I get 5 amps there and there. And here I get 10 volts across a 1 ohm resistor, so I is V over R. So I get 10 amps up here. So the power of bulb 1, I'll just do VI, is going to be 10 volts times 10 amps. That's equal to 100 watts. The power in bulb 2 is also going to be VI. That's going to be 5 volts times 5 amps. So it's 25 watts. So I have a factor of a half here and a factor of a half here.
So 10 volts on that T2, that's what the problem is.
Yeah, you have to have 5 volts because they split that voltage. All right. I need to be really good at answering these types of questions. I mean, not just for this class, but for moving on into like various standardized tests that you might take, the GRE, the MCAT, whatever. These types of questions are really popular. And they're good. They help to make sure that you understand. All right? We will come back to this after we do series circuits, or combination circuits. Let's do this next little question, this MCAT example. So consider this circuit. What happens to the total current if you add this resistor? So I'm adding this resistor R, and I want to know what happens to the total current. That is the current that comes off of here. You can click in on this. Does the total current increase? Does the total current decrease? Or does the total current remain the same? So here I'm asking about the total current. What does it do? Does it increase, decrease, or stay the same when I add that resistor R? We'll make this our last question. I'll hand back your exams. I want to show you a quick thing on it. All right, I'll stop at 45. Okay, so you want to ask yourself, what happens first of all to the resistance of this branch when I add a resistor in parallel? What happens to the equivalent resistance of that branch? Does it go up or down? It goes down. So the equivalent resistance of this branch actually goes down, right? Oh, what did y'all put? Y'all put A? Yeah, so that's right. That's fine. Yeah, I thought y'all got it wrong. No, A is right. Sorry, I was thinking about something else.
I mean, I was a little bit concerned because I went back to that question that is similar to that one. And you put increase, and I'm like, is he going back on this?
Yeah, I changed my mind. Yeah, so it does increase. Okay. So 8:15. I'm going to hand back your exams, and I want to just quickly go through that capacitor circuit because a number of you got it right, which I was really glad for, but some of you didn't get it correct as well. So a number of you didn't get it correct. So I want to show you all that, but let me hand it back first, and then don't leave. Just hang out a few minutes.
Chris?
Hunter.
What's the limit of expert in infinity? I really don't. I know I got that one wrong. $800 to run a computer in 2 minutes.
Folks, I put the solution online, but I just wanted to go quickly, just sort of how you redraw that circuit. I'll be good to go in just a second. So if you go, you can find the video for this. Oh, we're having 5 exams, not 3. Y'all know that, right? Despite what it says there. So when you redraw this, and as I told you in class, it's better if you I find that it's easier if you start from the positive side of the battery there, and then think about redrawing it. So I have the battery, and then I come along here, and I have a junction. Let me clear this. So I have a junction that splits into 2 pieces. So right here corresponds to right here. See, I'll take the top one first. I go to C3, which is equal to 6. And then notice right here it splits again. So I have another junction. That's C4 and C5. And notice both of these go straight back to the battery after I leave there. So I'm going to bring those back together. And then in the bottom part, I have 2 resistors, C1 and C2. Those are both 4 microfarads. And then it comes back to the battery. So once you get that, it's a lot like ones that we've worked. And then it actually becomes pretty simple because C4 and C5 are 1 and 2. So these combine to give me a 3 microfarad capacitor. And then these 2 combine to give me a 2 microfarad capacitor. These 2 combine to give me a 2 microfarad capacitor as well. And so my circuit now will look just like this. I have a 2 and a 2. Microfarad capacitor, which gives me an equivalent capacitance of 4 microfarads. All right, and then I'll leave you on your own. You can go through and see how all the voltages are distributed. But we worked a problem very similar to that. You know, on this circuit, it might be a little easier if you think about this. I think the diagonal thing just really threw a lot of people off, having this C5 be diagonal like that. I think it might be easier if instead you draw it like this. All right, that's the same circuit. And I think we might have worked a circuit very similar to that in class. I can just move C5 up. Y'all follow how I can do that? I'm not really changing the circuit at all, just moving it a little bit. All right, folks, I'm letting you on a little bit early, so if you have questions, you can ask me about points or whatever on the exam. But y'all have a good weekend, okay? We'll probably be in Chapter 4 for another few days, and then we'll move on to Chapter 5. So think about your homework. You're doing your homework. Have a good day.